Okay, now this is an alternative to using discs or washers horizontally, because a lot of times we don't like to draw the rectangles horizontally. Okay, there are advantages to using this method, but it's not required. Okay, so let me just write this down. This is not tested on the AP test, so you don't have to learn it. If you want, you can stop the video right now and be done. But you may like this method better. There's a few less calculations to do, perhaps, and maybe it makes more sense to you. Okay, so we're just going to go through it real fast. And we're going to do this on the exact same problem we just did because we know the answer, and we should compare to see if the answer comes out to be the same. So this is x equals 2. Again, we're going to use this as the axis of rotation. But this time, instead of drawing my rectangle perpendicular to the axis of rotation, I'm going to show you a method that lets you draw the rectangle parallel to the axis of rotation, which you may like better because you can leave things in terms of x rather than be in terms of y. All right, now, the first thing to notice is that when you rotate this rectangle about the line x equals 2, we get a interesting looking shape. Okay, the shape looks like a toilet paper tube once the toilet paper's all been removed. Okay, it's a very thin shell. It's like a cylinder, but it's got almost no depth to it, no thickness to it. Okay, so it's a basically big open cylinder with a very small shell, and we call this a cylindrical shell. Okay, or we just call the technique volume by shells for short. Okay, so you've had volume by discs, you've had volume by washers. The optional technique is called volume by shells. So here's our cylindrical shell, our toilet paper tube. We have some dimensions here. We have a radius and we have a height. And the question is, what's the volume of this figure? Okay, so here's how we're going to derive the volume of this thing. I want you to imagine that you took scissors and you cut the toilet paper tube on one of its ends, and then you flattened it out. Okay, if you flatten it out, it's going to look like a rectangle with a very small amount of thickness to it. So it's a rectangular prism. Now, if we copy down the dimensions from the figure on the left, this is the height. The thickness would be our dx or our dy, but it's going to be dx for us because we're not going to do this sideways. We're only going to do it vertically. And then the question is, what is this distance right here? Okay, well, if you look back at the figure, that's the distance around the top of the cylindrical shell. In other words, the circumference of the circle, which is always known to be 2 pi times the radius. So the volume of this figure is going to be 2 pi r h dx. And a way that was taught to me to remember this formula is 2 pi rat. Okay, where r stands for the radius, a stands for altitude, kind of like height, and the t stands for thickness, like the dx, the dy. Okay, now let's real quick label what these things are. Okay, what is r? R is the distance from the axis of rotation to the rectangle. A, altitude, is the height of the rectangle, and your thickness is going to always be the dx, because we're not going to do this the other way. So let's go back to our figure here, and let's talk about what we see. Okay, first of all, let's label some coordinates here. So this is going to be x comma square root of x, the red curve. That would be x comma x squared. And it doesn't matter where you put the dot on the axis of rotation. I'll just put it up here, and we'll call that x, sorry, not x. That x coordinate is always 2. Okay, so this would be 2 comma, and since I made it parallel with the dot here on the left, I'll just call it 2 comma square root of x. All right, so remember, r is the distance. The radius of rotation is the distance from the axis of rotation, which is here, to the rectangle. So that distance is going to be 2 minus x. The altitude, or the height of this rectangle, is the distance between these two dots right here. So that's square root of x minus x squared, and your thickness is dx. So our volume of a typical cylindrical shell is going to be 2 pi times 2 minus x times the square root of x minus x squared dx. And so the volume of the entire solid that gets formed is going to be 2 pi times the integral, again from 0 to 1, of this volume expression. 2 minus x square root of x minus x squared dx. Now, what are the benefits of this formula? Obviously, number one, you don't have to necessarily go sideways. Number two, there are no quantities being squared. So that's kind of nice sometimes because we don't necessarily want to have to expand binomials if we don't have to. And you'll find from time to time that that makes doing the integration nearly impossible. All right, let's go ahead and crank out what this is going to be, and we know what the answer should be so we can compare. First, we're going to expand the inside of this quantity. So we have 2 square roots of x, which I'll write as 2x to the half, minus 2x squared, minus x to the 3 halves, which comes from x times the square root of x, and then plus x cubed times dx. Okay, now antiderivatives. So we have 2 pi. This is going to become 4/3 x to the 3 halves minus 2/3 x cubed minus 2/5 x to the 5 halves plus 1/4 x to the 4th, and we're going to go from 0 to 1. A little bit more room here. 2 pi times, in brackets, big parenthesis minus big parenthesis, 4/3 minus 2/3 minus 2/5 plus 1/4, and then these all become 0, which is nice. That won't always be the case. And now let's see what happens here. We need a common denominator. So 4, 5, and 3 will all go into 60. This would be, well, first of all, 4/3 and 2/3 can become 2/3, so that's going to become 40 over 60. Okay, minus 24 over 60 plus 15 over 60. So we now have 2 pi times 40 minus 24 is 16 plus 15 is 31. We multiply by 2, we're going to get 62 pi over 60 or 31 pi over 30, which is what we had when we did using the method of volume by washers.